Okay, I sort of roughly remember, vaguely, I'm aware of this. So if you live in a region where the temperature at night gets below freezing, you could use this in quarrying stone, rock. Okay, so let's say here is a mountain, and you want to cut off this. You like to cut off this slab. So what you do is, so again, this works if the temperature falls below freezing. So you cut a groove, then fill this with water. And then at night when the water freezes, the forces are so great that this cracks. That's the idea. Okay? And so we'll see what kind of forces are involved. Okay? All right, so most things, when you decrease the temperature, what happens to the volume of the stuff?
It decreases.
It decreases. Okay? It turns out that when you take water and you freeze it, so you're decreasing the temperature, ice expands. Okay? And the volume changes significantly, changes by 9%. Okay, so it turns out that the density of ice is about 90% the density of water, and that's why it floats. Okay? So, for instance, if you took liquid iron and froze it, that chunk of iron would sink in a sea of iron. Did you guys understand that? So most other liquids, the solid would sink. But ice floats, of course. Okay. So here's the deal. You guys might have experienced this in your refrigerators. So what we'll do is we'll take a container, sealed container, and fill it to the brim with water, seal it and all that, and then freeze it. Okay. So what will happen? The ice is expanding and it'll apply a force like that. It wants to bust open the container. And we'll calculate the force you would have to apply to keep it inside the container. Okay. And you'll realize that soon that no container can hold it. Okay, so when water freezes, its volume increases by 9%. So if you want to keep that water, you have to apply a force such that its volume decreases by 9%, okay, to fit it in that container. What force per unit area is water capable of exerting? So what force per unit area is the water capable of exerting? This is the water force, this is the applied force on a container when it freezes. Okay. So if you look up your notes, the bulk modulus is negative force per unit area. Change in volume divided by the volume. Now you'd have to decrease the volume, this would be negative, and that's why that negative sign is there. Okay. Now, so ice is expanded to keep within the container. By what fraction did you decrease the volume? By 9%. So this is going to be, so bulk modulus is F over area, and that decreased by 9%, so this number is negative 0.0905. So the force you have per unit area you have to apply, which is the pressure, is 0.0905 times the bulk modulus. And the bulk modulus for ice is gigapascals, 9 gigapascals. Okay, so 0.0905 times 9, 10 to the 9. Giga is 10 to the 9 pascals. Okay. All right, so let's do this. the force per unit area that the expanding ice exerts is 8,000 times 10 to the power 5 pascals. What is this guy? That's 1 atmospheric pressure. Okay? And so now let's put this in perspective. Do you guys know atmospheric pressure in PSI? So we're trying to give this number a meaning. Okay? So 1 atmosphere is 10 to the power 5 pascals, and it's about 15 psi. What does this stand for, 15 psi? Pounds per square inch. So what this means is, here's a square inch. Okay, air molecules bouncing off this square inch are applying a force of 15 pounds. That's what atmospheric pressure means. Okay. So, all right. So what is the area of this page? It's roughly 10 inches by 10 inches. That's 100 square inch. So the force the atmosphere exerts on this page is 1,500 pounds. That's 1 atmosphere. So if the container, the side of the container was this big, the force 1 atmosphere would exert would be 1,500 pounds. The expanding ice is exerting 10,000 times that force. Okay. So 1.5 million pounds. All right. Let this sink in. I can't see a box. Yeah, okay, so let's put water in his bag. Hold up your bag, please. Hello there? You. Hold up your bag. So let's say we fill that thing with water and freeze it. On each side, the force would be 1.5 million pounds. Do you guys know the thrust for the Saturn V rocket? That's why you have a physics teacher to tell you that. 7.5 million pounds. Screw the rocket, we can just freeze water. It is absolutely amazing. So do this experiment. Take a plastic bottle, fill it with water, screw the cap, throw it in your freezer. Okay. And then let the water open the cap, right? Okay. All right.
Quick question.
Mm-hmm.
What happened to the negative sign at the beginning?
So the ice expanded. To keep it in the container, you decrease its volume. This was negative.
Oh,
So you had to. All right, so here. How's that?
okay, then.
All right, we'll do this. Okay, so a disc between vertebrae in the spine is subjected to a shearing force of 600 Newton. 600 Newton. So essentially, so there is a disc, shock absorber disc between vertebrae, you know. And so let's say when you bend over like that to lift something, you're exerting a shearing force on the disc. All right. How many times do you want to be able to bend over and lift stuff? Millions of times. That disc had better have a lifetime warranty on it, you know. So who do you complain to, right? If it doesn't work. All right, so 600. So here's the disc. Find its shear deformation using the shear modulus of 1 gigapascals. The disc is equivalent to a solid cylinder, 0.7 centimeters high, So the height is 0.7 centimeters and 2 centimeters area, radius. All right, so what you're doing is this is the shearing force. You're applying equal and opposite forces. The two vertebrae are applying equal and opposite forces. And what happens? It deforms like so. Okay? And then when you stand up straight again, it'll go back to its original shape. Okay? And of course, you want this to be repeatable millions of times. So what is the question? Find its shear deformation. So what they want you, this is delta x, and this is height. Okay. So the shear modulus is given by force divided by area. The area is this area, the area of that disk, divided by delta x, and this is the shear deformation. Okay. So delta x by h is F over A. Okay, this is what they're asking you to calculate, but let's calculate delta x. Okay. We'll we'll do that, delta. Because that will make, okay. F over A, so 600 newtons. The area this is a circular, okay, so from the top, here's how it looks, and R is the radius. Pi r square, R is 2 centimeters, and we gotta convert that to meters, and divided by the shear modulus, which is 10 to the 9 Newton meters. I'm going to keep this there. Okay, let's take care of powers of 10. This is 10 to the minus 4. When it comes to the bottom, that leaves 10 to the 5 there. Okay, so this is 600 newtons divided by 4 pi times 10 to the 5. And the meter square, Newton per meter square cancels the Newton per meter square. So this is a dimensionless number. Okay. And this is equal to Okay, so that's how much it deforms. So if you want to convert that to percent, you would multiply by 100. So 0.05%. Okay, that's how much it deforms. Yeah. So the disc is pretty good, and the shearing force, 600 newtons is your weight. That's a large shearing force. Okay, and it deforms very little. So let's calculate the actual delta x is h times that. And h was 0.7 centimeters. Centimeters, 1 centimeter is 10 millimeters, so 4,000th of a millimeter. Okay, probably the thickness of a fine hair. That's pretty good. So did you guys understand that? The disc, the top and the bottom surface shift by the width of a hair. Okay. All right, any questions on that? But still, if, I don't know, if you work in a place, that's why they tell you don't lift objects like that. You lift objects like this. So you don't want to apply shearing forces to your disc. Okay. All right, one more problem and then we'll move on to the next chapter. Okay. A suspender rod of a suspension bridge is 25 meters long. So okay, so this is what they're talking about. Okay. So this guy is 25 meters long. And of course, when a truck drives by, this stretches a little. Okay. Every time a truck drives by, this stretches, and that's what they want to know. So if the rod is made of steel, what must its diameter be so that it does not stretch more than 1 centimeters when 25,000 kg truck passes by it? Assume that the rod supports all of the weight of the truck. Okay. So essentially they're saying that, so here's the model. So you're suspending the truck from the rod. Okay. Young's modulus is force. So the force that you applied, which is the weight of this thing, and area A is the area of cross section, and the stretch divided by length. Okay. So what must be that diameter? So area is equal to F over Y delta L over L. Okay. Pi r squared Okay, so that's the radius of that rod, of that steel beam, or steel. Well, it's actually, those things are twisted steel cables. Okay. So have you guys driven over suspension bridges? There's one in Jacksonville, which is kind of pretty. Oh, yeah. You don't like it? The 9A bridge?
The Dames Point is the least pretty of the Jacksonville bridges.
Which one?
The Dames Point, that's the suspension bridge.
On 9A.
Yeah.
It's
the one on
least
north- It's the one on the north side.
northeast.
Yes.
It's very pretty.
The surroundings are pretty, the bridge itself is.
I love the bridge. All right. Yeah, I would love to ride my bike on that bridge.
That's fair.
Yeah. All right, so let's calculate the radius of that bridge. I mean, radius of that cable. Okay, you guys understand what we're doing? Okay. And so you see, as an engineer, you're limiting the stretching to 1 centimeter. Why are you doing that? I'm sorry? So remember, okay, well, let's, hmm? Yeah, so let me go to the lectures. What's that?
I was gonna say it either deforms or the tensile strength is.
Yes, so what you want to do is you want to be in the linear limit. And so you want to be there. You want it to behave elastically forever and ever. Okay? So that's what decided on the 1 centimeter. Okay. All right, so now let's figure out the radius of the cable. All right. So the force is the weight force equal to mg, what you're supporting. Okay. Pi y delta L by L. Okay, and I'll write this L on top now. That's 25,000 kgs. G is 9.8 meters per second square. L was 25 meters. Pi delta L was 1 centimeters, which is 10 to the minus 2 meters. And Y, we have to look up Y for steel. Okay, so there we go. Young's modulus steel, 20 times 10 to the 10 pascals. All right, so let's take care of powers of 10. This is 10 to the 11, 10 to the 9, and we'll spend 10, so 10 to the 6. So 10 to the 6 at the bottom. Square root of that is 10 to the minus 3. Okay. So 10 to the minus 3 outside. This is in meters. And you have 25 square times 9.8 divided by pi, 2 pi. You guys with me on that one? So 31 millimeters, okay, is the radius. Um, so the diameter is 62 millimeters, which is 6.2 centimeters. 6.2 centimeters, about that thick. Okay. So that's the thickness of the cable. All right, guys. So if you wanted the cable to stretch less, what would you have to do? Everything else being the same.
Increase the diameter.
Increase the diameter, okay? So you want this to be less, that has to be greater, R has to be greater. Okay? All right, so we'll stop